This video follows on from the other uniform circular motion exam style questions I've been answering, so we're continuing from there. In this question it says figure 1 and figure 2 each show a car travelling in a horizontal circular path. Draw and label on figure 1 and figure 2 arrows to indicate the other forces acting on the car. Right, okay, so I'm just going to redraw this because this is quite a dark object to put arrows over. So if I just redraw the car as a box, and there's the horizontal road, and it already is labelled that there is a weight, and the weight would be supported by the surface, so there'd be a normal contact force equal and opposite to the weight because this car is not sinking through the ground. However, the vertical forces are balanced, but there must be an unbalanced horizontal force because we need a resultant force in this direction, which will be our centripetal force to cause the car to move in a circle. Now, if you think about looking down on this car, it has a linear velocity wanting to move it in this direction, but there has to be some force that causes it to change that direction. And what this comes from is the frictional force between the surface of the tyres. So there is a frictional force towards the centre, and that frictional force is our centripetal force. Now in figure 2, there is a banking to the road, and so we're going to discuss what effect that will have on our car and its ability to go around the corner. So here's the car again, except for this time there is an angle for the track, the banking of the track, that's theta. The weight of the car will act vertically down again, but the normal contact with the surface of the road, normal being perpendicular to the surface, this can be thought of as if you take the weight and there is a component vertically and horizontally. So the normal contact is can be thought of as having a component vertically and a component horizontally, and the vertical component, so this is theta, the vertical component, which is n cos theta, well, that should equal the weight of the car. Okay, so they balance out vertically. However, there's nothing to balance out the horizontal component, and the horizontal component will be n sine theta, and it's this that's causing the car to move in a circle. Okay, so there is actually a force due to the contact of the ground that gives it a bit of a push in the direction towards the centre. Right, so that's our centripetal force again. State the possible origins of the centripetal force on the car in figure 2. Okay, so in case you were wondering about frictional forces, obviously there is friction because this will want to naturally drop down under the weight of the object and move down the ramp. So there has to be a frictional force that's part of this. So in terms of answering this question, possible origins of the force, often between surfaces there'll be friction. It's coming from partly the reaction force that we discussed, the normal reaction force. And I think that'll do for that. Okay, so origins of the friction, reaction force, horizontal component of either of those forces, and then you'd sum those forces up. Okay, so the overall resultant would be partly due to the track pushing on the cart and partly due to the frictional force between the tyres and the track. So you'd have to sum those forces up. Part B. Figure 3 shows a motorcycle stunt rider travelling around a track in a vertical circle of radius 5.2 metres. A possible cue when the speed is the minimum necessary to keep the motorcycle on the track with the contact with the track. The centripetal force is supplied by the weight of the motorcycle and rider. The combined mass of the motorcycle and rider is 220 kilograms. Calculate the minimum speed which will keep the motorcycle in contact with the track at Q. Okay, the acceleration due to gravity is 9.8. Okay, so if we think about the forces acting on the motorbike, I'm just going to draw a very simple motorbike circle. The weight and the normal contact between the bike and the track, they would sum up, W plus N, they would sum up and they would be our force acting towards the centre, our centripetal force. So it's going to be mv squared over r. And when we suggest a minimum speed, we're suggesting the point where there is contact. Any slower and there will no longer be a contact force between the track and the rider and the motorcycle. So when this becomes zero, what we're saying is that the weight of the object is equal to mv squared over r. So the weight being mg, mv squared over r, cancel the masses, multiply it by r, square root it. The minimum speed would be the square root of gr. Now r is 5.2 and g is 9.8, so it's the square root of 9.8 times 5.2, which comes out as 7.1 meters per second. Okay, so that's the minimum speed. Obviously I've discussed this type of scenario in the theory video. This is just going through the exam style question. So we've got next question. Question 6 is a roller coaster question, but a lot of this question's to do with energy, and then the final part talks about a circular motion. But we can go through it all anyway. So it says, in the figure below shows a car on a roller coaster track. The car is initially at rest at A, then it's lifted to a height B, and then finally it'll move down this track and go past C. The car with its passengers has a total mass of 550 kilograms, and it takes 25 seconds to lift the car from A to B. Okay, so through a vertical height of 35 meters. Calculate the power used in lifting the car and its passengers from A to B. Include an appropriate unit. So, when we talk about power, we mean the rate of energy being transferred. So, this energy is how much gravitational potential energy it has increased by, because we're moving it through this vertical height. So we mean mgh over t, and the mass is 550 kilograms, g is 9.8, height vertically is 35 meters, and it took 25 seconds to transfer that energy. So that comes out as 7.6 times 10 to the 3, 10 to the power 3 watts. But what I could do is replace that with a prefix, so 7.6 kilowatts. Okay, 7.6 thousand watts. B. The speed reached by the car at the bottom of C is 22 meters per second. The length of the track is 63 meters. Calculate the average resistive force acting on the car during the descent. Give your answer to a number of significant figures consistent with the data. Okay, so well, everything's two significant figures, so my answer is going to be two significant figures. So we have to calculate how much gravitational potential energy it starts with, how much energy is converted to kinetic. The difference in those energies we'll say is a loss in energy, or the energy that's gone into doing work by the resistive forces. So obviously work done is important, force times displacement. So we can work out the resistive force if we know the work done, and we're suggesting that that work is the loss in energy from having an initial gravitational potential energy, taking away the energy that went into the motion of the cart, and then obviously dividing that by the displacement of 63 meters. Okay, so S is 63 meters, and then M was 550 kilograms. And what else do we need? G is 9.8 newtons per kilogram. H was 35 meters, and V at the bottom is 22 meters per second. 22 meters per second. So if I plug all those numbers in, I've got 550 times 9.8 times 35, and I'm going to take away the kinetic energy. Half times 550 times 22 squared, and that would be divided by 63 meters. If you do put this into a calculator, you'll get 189 kilojoules of initial gravitational potential energy. The kinetic energy, if it's traveling this fast, comes out as 133 kilojoules. And then we're going to divide that by 63, and obviously the difference then is 56 kilojoules divided by 63 meters, and that comes out as 890 newtons. So 890 newtons, so two significant figures. Okay. Next part. Explain why the resistive force is unlikely to remain constant as the car descends from B to C. Well, it starts off at an initial velocity of 0. So in terms of the air resistive force, that would be 0 because it's not moving through the air, it's not moving past the track. So really we just need to mention that air resistance increases and frictional forces, that's between the cart, the track, and the roller coaster itself, forces increase, and this is as speed of, I'll call it a cart, roller coaster, increases down the track. Final part. This is the circular motion question. So it's saying at sea, a passenger of mass 55 kilograms experiences an upward reaction force of 2,160 newtons when at that speed of 22 meters per second at the bottom. Calculate the radius of curvature of the track at sea. Okay, so what we're saying is at the point where it's at the bottom at sea, okay, so there's our roller coaster. And just bear in mind that this is part of a circle of radius r. However, that's not what the track does. The track obviously goes down and then comes back up. And so what we need to do is we need to think about summing up the forces. So it's got weight acting down, normal contact acting up. The normal contact has to be greater because you have to have a resultant force towards the center of the circle. So we've got N minus W. That's our centripetal acceleration force, sorry, so that's mv squared over r, and we're working out r, so we're going to rearrange r equals mv squared over, and we're going to divide, so we brought r up, we're going to divide by n, and we're going to minus w, and I'm going to call w mg, so that's how we calculate the mass, the weight, because we have mass, 55 kilograms, v is 22 meters per second, N is 2,160 newtons, G is going to be 9.8 newtons per kilogram, and so putting the numbers in, we've got 550 times 22 squared divided by 2,160 minus 550 times 9.8, and that comes out as 16.4 meters. So the radius of curvature of this part of a circle, this arc, is 16.4 meters.